So now that we have discussed or known that these are the two problems, how to avoid them? Let's start with the first one. How to avoid cost of polling. Polling itself is a useful operation because you have to wait until the device is busy, right? It has its own purpose. So if we just omit polling, then we are breaking the task, or then we wouldn't be able to complete the task. Because if the device is still busy, you don't want to just throw the data off somewhere. Doesn't matter if the device is busy and return the CPU process. In that case, you would lose that data. So polling is important. You cannot just omit polling. But we want to omit is cost of polling or reduce the cost of polling. How do we do that? Spend some moments or a minute to think over that here. If you recall the concepts that you would have learned in your operating system courses that you would have taken earlier, or if you are well versed with operating system in general, you would have heard the word interrupt. So one way to avoid the cost of polling is lowering CPU overhead with interrupts. So when we are using interrupts, that is mainly hardware interrupt. When we say interrupt, because we want interrupts to be fast, what we are doing here is instead of polling, the device repeatedly, the OS can simply issue an interrupt. Now, put the calling process to sleep after issuing an interrupt. And while we have put our calling process to sleep, we could context switch to another task. Finally, when device is finished with operation, it will raise the interrupt. So as soon as the device raises the interrupt, CPU jumps into corresponding interrupt handler and wake the process waiting for the IO, because now whatever operation, read or write, that this process wanted, it's ready. So now this process could further continue. And thus, by this concept of interrupt, raising an interrupt, and having this process of interrupt allows the operating system or the CPU no longer to wait and waste its cycle while the device is busy processing its island. So think of this interrupt, one of the easy or analogy that I could give to understand the process of interrupt is many of you would have worked either as a teaching assistant while you are handling a lab of students where multiple people are working in front of you and you are supposed to monitor their progress, solve their doubts. If they get stuck, help them with overcoming their problems and then continuing their work. Or many of you would have either supervised an exam where multiple students are writing and you are there in that room. If any student have any issue, then you help them with that. So now imagine that you just have one student to monitor. Imagine you are the monitor, right? And imagine you have just one student whom you are monitoring. In that case, you could literally, if it's a work done on computer, you could keep looking at the screen of the computer, keep looking at the progress the student is making. And as soon as the student proceeds with a wrong step, you could correct the student. So that's something like polling, because you have your continuous attention all the time while the student is working on something. Now imagine that the number of students increases to 2 from 1. Still, you could manage. Our human brain is thankfully a very powerful machine. So we could manage to monitor 2 tasks or 2 screens at once and keep looking at if any one of that gets stuck into any problem or does anything wrong, then you could correct them immediately. That's like polling still with 2 processes going on. Now from 2, imagine that the number of students increases to 50. How would that be? We cannot look at 50 screen at once, right? Even if you're looking at 50 screen at once, probably you wouldn't be able to identify the problem that happens in one of that 50 screen at any given time. So what you would do naturally is you would give all your attention to one student and just spend some moments, see if that student is doing all right. Then you would walk forward, you would see the second student is doing all right, you would walk forward, the third student is doing all right. So on and so forth, go until all the rows in the classroom is done, or go up to the back of the classroom and then walk back front again. So you're doing one by one. It's still polling where you yourself are proactively going from one student to another and seeing if they have a problem, and then you are helping them with that problem, if that's the case, and then proceeding forward. Now, in this process, this process is very similar to the process of polling, because you are handling one task at a time until you resolve the issue with one student, then you move on to the other. But what is happening is people are wasting their time. They could have an issue, they need your help. That issue could be very small, but they need to wait until you get to them. And they might be the fortunate student sitting as a last student in the last row of the classroom while you are in the first row still. So that is the problem with polling, the waste of time. Now, the process of interrupt is you tell these students, there's 50 students, that, hey, if you have any problem, raise your hand and I'll come to you. That's the smart idea, right? Because that's exactly as what we just wrote in this, we just saw in the statement over here. Instead of polling the devices repeatedly, the OS can issue an interrupt. So you're asking students to issue an interrupt. And CPU, like you would until students they have their hands down, that means they are making progress on their task that you gave to them on their own, right? That's something like an IO device working on an IO operation that's already been issued to that. As soon as an IO device is done with this operation, it will raise an interrupt. That's equivalent of raising a hand. As soon as the student raises a hand, CPU, which is you in that classroom, jumps into the corresponding interrupt handler and wakes the process waiting for the IO. Thus, you would go to the student and say, okay, are you done? What's an issue? If you are done, you may please leave, because then you are done with whatever you had to do today, the task assigned to you. If not, then if you had some problem, but whatsoever. But the idea of this idea of interrupt or reducing the cost of polling is inspired by a very basic human logical sense of thinking, right? So many such problems could be solved by just our common sense. That's what we call humans. Now, I would spend a bit more time on this problem at hand and try to draw and show you how these cycles are wasted while we are stalling or in the process of polling versus in the process of interrupt, we are able to save those cycles. So let's have our CPU and disk. Those are the two components. Now our CPU number one represents like process, the task done by process one. And each instant represents maybe the time instant or as time proceeds every second. So CPU is processing something, it's processing something, making some progress with process one in this first 4 seconds. And then now it needs some data. So maybe it's waiting for a read. So while in order to read, now disk is processing something. So let's say that disk takes 3 seconds to um, give that data to CPU. Or in order to fetch the data from the disk, it takes 3 seconds. So for this 3 seconds, now CPU here in polling was just stalling because it was just asking the disk, hey, are you done? No. Are you done? Not yet. Are you done? Not yet. And then finally, when it polls for the 4th time, then disk says, okay, I'm done now. Here is your data. So then CPU returns back to processing and makes progress with whatever data it receives. Now, in case of interrupt, we still have our CPU and disk as our two entity, and thinking of that same scenario, what happens is we have our CPU processing on something until it doesn't need any more data, but as soon as when it comes to this part where it wants to read some data from the disk, now your disk is busy working on this process one for this another 3 seconds, but because of the mechanism of interrupt, what happens is while disk is busy working on fetching this data, CPU just puts an interrupt and can be occupied or can go ahead and complete some another work with some another processes. So the CPU starts working on process two. And then as soon as the disk completes the task, it is done with fetching the data, it raises an interrupt that, hey, I'm done. Then CPU jumps into corresponding interrupt handler and wakes the process waiting for the IO. That's nothing but process one. And so from here, again, the process one CPU gets occupied in process one and completes it. So in this way, we, rather than stalling for this 3 seconds, we use that 3 seconds for something else that CPU also had to do. Like when you are monitoring 50 students, you don't have to monitor just one student, but 49 others. So you always have something else to do. In the same way, CPU always have something else to do. So this clearly illustrates the difference between process of polling and how using interrupt we can reduce the cost of polling.